Well, hello, listeners. Welcome back to the amazing astronomical alphabet with me, Andy Briggs, and my esteemed co-presenter, Daz. How are you doing, Daz?
I'm fine, thank you very much. Had one of those weeks there. Everything's gone to pot. I've lost all my paperwork for this show, but we will muddle on. And
Okay.
if I can't remember what it is, I'll make it up anyway. It'll be entertaining.
Fine,
anyway.
fine. Just entertain us,
No.
Daz. Okay.
No.
Well, I believe this week it's your turn to start. So E is for da da da.
Drum roll, please. It's for Albert Einstein.
Ah, right.
You're telling me you didn't have that one?
No. Because
okay then. No, we might get away with this then.
we might.
Because we were a bit worried that with the ease we might duplicate, but this is a good start. A good start. Now I'm only going to give you a short run through of his life. I'm not going to actually, because as we all know, Mr. Einstein, one of the geniuses of the 20th century, gave us lots of laws and things. About gravity, about light, about the fabric of space and everything like that. So we all know who he is. If you don't know who he is, where have you been? But what I'm just going to do for the minute is I'm just going to give you a quick and abridged run through of his life.
Okay.
And then what we will do, and you'll probably see later on why I've only just started with a quick resume of his life. But hopefully it'll become clear.
Okay.
So, Mr. Albert Einstein was born in Ulm in southwest Germany on the 14th of March, 1879. He was the second child of Hermann Einstein. That's a pretty good German name, isn't it? They're Hermann. Founder of an electrical engineering company, and his wife, Pauline. The family, who were non-observant Ashkenazi Jews, soon moved to Munich, where Albert later went to school. Age 17, Einstein entered the Swiss Federal Polytechnic School in Zurich to train as a teacher of physics and mathematics.
Can I just stop you there one moment?
Yes, certainly.
Just one interesting thing about that. The first time he tried to get into the Polytechnic, he actually failed the entrance exam.
Oh, did he?
Yeah.
Well, it's like Jocelyn Bell, wasn't it? She failed her 11 plus. So, but it just goes to show a failure at the beginning doesn't mean you're not going to go on and do big things.
Well, he was actually considered a bit backward at school by his teachers.
I can understand with that hair and that stuff.
Einstein didn't utter his first words until he was nearly 3 years old. Yeah, it's true.
Well, he's holding back, wasn't he? He could have given us far more if he'd just spoke a little bit earlier.
Well, he was obviously thinking a lot, Daz.
Exactly. Yeah, he knew that these big things, and he was sort of like working them out. Basically, he was making sure he knew what he was talking about.
Yes, that's exactly it. Anyway, sorry to interrupt. Please continue.
No, that was interesting. I didn't know that. But like I said, it's just interesting.
He never showed at school any real academic promise whatsoever.
Yeah, because there is later. Well, we'll talk about something in a little while.
Okay.
But yes, so he went to where did I say he was going? Oh, into the Polytechnic in Zurich. It was there he met his fellow student Maliva Morik, who he married in 1903. Now, I'll talk about what I was going to say earlier, because a lot of people seem to think that she was an inspiration and possibly the instigator of a lot of his thinking in later life. So I know she did help him a lot, but whether or not it's just one of those things. Sometimes they say, oh, well, the missus did it for him, really, because they say behind every great man there's a great woman.
Well, she was quite a determined young woman. She was very, very independent and determined in her own right to make a mark in physics, and she didn't suffer fools gladly. Yeah. And when she first met Einstein, she actually wasn't that keen on him, thought he was a bit full of himself. But she was equally, as determined, as stubborn as Einstein. So, in the end, they probably made a good pair.
Exactly, and of course we're talking about 1903, so maybe with the same with what's happened to other women in physics and stuff like that. So they basically could only get their work out there through the husband. So
yes, absolutely.
Maybe she was the power behind the throne there. We don't
Maybe
know.
she was.
But whatever it was, they did a wonderful job. So as I said, they married in 1903. In 1987, newly discovered letters between the two revealed that they had a child out of wedlock in 1902. Oh, scandal.
Is
I
that
didn't know
wedlock in
that.
Germany?
Yeah, wedlock, yeah. Yeah, wedlock holiday.
Yeah.
And it's a bit of scandal. I never knew that. Though the fate of this child is was a girl, is unknown. She may have been adopted or died in infancy. The couple later had two sons, Hans and Eduard, before separating and eventually divorcing in 1919 when he married his cousin Elsa Lothenwell nee Einstein.
Yeah, she was his true love. She was the one who he'd been, in love with. Well, since childhood, they were the best of friends in childhood, and
because they were cousins and stuff like that. So,
right.
So anyway, after graduating, Einstein spent a frustrating 2 years trying to secure a teaching position, and eventually ended up working at the Swiss Patent Office.
Yeah,
it was here and in his spare time that he made his early discoveries, including the remarkable series of papers of his Annus Mirabilis in 1905. This led to his appointment in 1908 as a lecturer at the University of Bern, Switzerland, which was swiftly followed by a professorship at the University of Zurich. By 1914, he was a professor at the University of Berlin, where he remained for almost 2 decades until the political situation in Germany changed and the Nazi government began to prohibit Jews from holding teaching positions in university. So he lived in some troubled times.
Indeed.
In 1933, he gave up his citizenship and emigrated to America, finding refuge at the Institute of Advanced Study in Princeton, New Jersey, where he remained until his retirement. Einstein is known not only for his remarkable discoveries, he was also an ardent music lover, and as we know, he played the violin. A pacifist, a champion of civil rights, and a supporter of Zionism. He died of an aneurysm in 1955, aged 76, and his ashes were scattered in an unknown location, although his brain has been preserved. So it's probably pickled somewhere on a shelf or something.
Well, the funny thing is that Einstein's brain disappeared for decades.
Oh, did it?
Finally found in a cardboard box under a water cooler in an American university.
Okay.
Absolutely true story.
Oh.
Nobody knows how it got there or why it was put there, but yes, Einstein's brain was missing. The physicist's brain is missing.
Yes, we know some presidents of brains that went missing.
Well, yes, well, we know some that never had any. Yes. In fact, and after he died, surgeons took his brain apart, basically.
Yeah, it was dissected. Yeah,
his brain was dissected to work out, to see if there was anything unusual about his brain that made him different to other people, that enabled him to carry out these incredible intellectual feats. But they didn't find anything. However, a recent revision of that in the last couple of years has found that, in fact, there was something different about his brain, that the connections between his left and right hemisphere were more dense and more plentiful than in most other people. So it's all to do with the connections, you see. So
it's not what you know, it's who you know.
Oh, that's right. Absolutely.
As long as the left side and the right side of your brain is talking.
But it's it's often said that the power of the brain doesn't lie in the actual cells themselves. It lies in the connections between them.
Exactly.
And this is what they think enabled Einstein to carry out what to us are amazing intellectual feats. Anyway, there we are. So
that's it. That's Mr. Einstein. As I said, it was a short introduction to him.
Yeah.
But hopefully it'll become clearer later why it was just a short one. So there you go. Thank you very much.
That's all right. He had amazing intellectual gifts, although he wasn't incredibly good at maths. He actually had to have help with his maths to write relativity from a colleague. I can't quite remember his name. A close friend of his was a maths genius, and Einstein got him to help because Einstein wasn't a mathematician. He was a physicist, but of course relativity is probably 100% understood by only a few people in the world, because the maths really puts people off. The classes that you can attend at universities in the maths behind relativity are meant to be just absolutely horrendous. Anyway,
you'd have to be pretty dedicated to sit through all of that.
Well, that's right. But he did distill all that maths down into what is the world's most famous equation, which is E equals mc squared.
MC squared, yeah.
Which demonstrates the interchangeability of mass and energy.
Yeah.
Matter and energy. So, many years later, people began to hope that what he worked on during the last decades of his life, which was the so-called theory of everything, which was an equation that describes, how gravity and light and everything are interrelated, and it will be an equation that could describe everything in the universe. And there was a hope of that for many decades, and people were hoping it was an equation you could wear on a T-shirt, that it could be distilled into that level of simplicity as E equals mc squared was. But it now looks as if that's never going to happen. That in fact, if we ever do come up with a theory of everything, it is going to be horrendously complicated. So there we are.
You'd have to be an extra large shirt.
Well, yeah, that's right. You have to get the XXL to wear that, I think. However, we will see. It's not going to happen, for
a long time. We know so.
I'm not optimistic that we'll have the theory of everything in my lifetime, certainly. No. So we will see. But yeah, thank you for that introduction to Einstein. His life story is quite amazing. He was, in fact, invited to become the first president of Israel when Israel was formed.
Okay.
Because of his pacifist beliefs.
Yeah, it said Zionism,
and he was asked by the Israelis to be their first president. He declined, basically saying that no, he wanted to carry on working and didn't want to get distracted by politics. So there we are. And he ended up at the Institute for Advanced Research at, is it Princeton or Yale? Princeton, I think.
Princeton, yeah.
Yeah. And somebody wrote about him that in his latter years, he wasn't getting anywhere with finding this theory of everything. And he walked like a ghost round the corridors of Princeton, which sounds a bit sad, really.
Yeah.
Because, his glory days were behind him, and this theory of everything he wasn't getting very far with. Not least of which was because, of course, he never really embraced the idea of quantum mechanics, and tried to get around it, but then discovered that he couldn't. That any full description of the universe, the so-called theory of everything, must include quantum physics, because as we know, the theory of that physicists are hunting for is the unification of relativity and quantum physics, the so-called theory of quantum gravity. And without the theory of quantum gravity, we're never going to understand the universe, and we're never going to understand things like black holes, other things in the universe. Right, back to me then. So here's a nice one for you, Daz. Now, last week we talked about the ancient Greek Democritus, which was very interesting.
Yeah.
And I've got another ancient Greek for you this week. The ancient Greek whose name was Eratosthenes.
Oh, okay then.
Eratosthenes. He was born in Greece in a place called Cyrene. That's now part of Libya, incidentally.
Yeah.
He was born in 275 BC and died in 195 BC. He was the librarian at the Great Library of Alexandria, which was at the time the world's greatest repository of knowledge. Nothing like it had ever been seen before in history. and unfortunately burnt down in a fire. And all that knowledge was lost, or most of that knowledge was lost. And history doesn't specify the cause of the fire, but the world's first and greatest library up until that point burned to the ground. Yeah. And with it, unfortunately, went most of Eratosthenes' work. So we don't actually have much of his original work to go by. Now, why I think is interesting is that he did many things in his lifetime, which we're familiar with today. He was the first person to calculate the circumference of the Earth, and he did this by measuring the shadows coming from Styx at midday in Alexandria, and can't remember the other place, somewhere far removed from Alexandria. And by measuring the length of the shadows, he managed to work out the circumference of the Earth. And he got it very, very close indeed. Now, don't forget, this was 3,000 years ago, Odd. And he managed to come up with a figure that was between 2.4, minus 2.4, and plus 0.8% out in accuracy. And that's nothing with him. That's our interpretation of how long the units of measurements were that they were using at the time, because we're not exactly sure. So however you look at it, he came up with a more or less spot-on calculation 3,000 years ago of the circumference of the Earth, which was simply by measuring the length of shadows from sticks placed in the ground. Amazing.
Yeah, that rings a bell. That and I'm just trying to rack my brain as well. You said, because you said it was in Alexandria, wasn't it? And yes. Where else? I'm trying to think where it was he did it. Yes, it
could have been Cairo, actually.
Yeah, because I was thinking of something to do with the pyramids and that. So
it could have been Cairo. It could have been Cairo.
Yeah,
that's easily Googleable. But his work wasn't just that. He was the first person to calculate the axial tilt of the Earth at 23.5 degrees, and he got that spot on as well.
Okay.
He was the first person as well to create a global projection of the Earth in a map. And, we're familiar with map projections like the Mercator projection and other projections, all of which are distorted because you can't represent a three-dimensional sphere on a two-dimensional map, as we know. But what he did with this projection, it was also notable that he included what he called parallels and meridians, which nowadays we know as longitude and latitude. So this was well in advance of his time. He actually created a map projection of the Earth using lines that were later identified or labeled as lines of longitude and latitude.
Oh, excellent.
Yeah, he was also the founder of the field of scientific chronology, which basically means putting historical events in the right order. He founded that study. And not content with that, he was the first person to calculate the distance between the Earth and the Sun. And he got that. Do you know a figure he got from that? 93 million miles, which was more or less spot on. And spurred on by that success, he calculated the diameter of the Sun. But there he went sadly wrong, because he calculated it as 27 times the diameter of the Earth, whereas the Sun is actually 109 times the diameter of the Earth.
Just a slight error there.
Yeah. But also, he invented the spherical astrolabe. Which, as you know, is a device. It's a spherical device it's a model of a system. In this case, the solar system, and that he made. And of course, in those days, the Earth was at the center of the solar system, not the Sun. But he was the first person to build an astrolabe that represented the Sun and the planets. In a spherical thing.
Yeah, because that's freaky, because I was listening to the radio earlier on, and on a well-known international television radio station, they were talking about the 100 great discoveries, and today was the astrolabe.
Wow,
so,
that's amazing.
Yeah, and but they were talking about more about they had one, and apparently it's from Spain. It was made in Spain because apparently that was the center for making these sort of things, because you had the merger of all the civilizations in Spain at the time. So that's where they started to, because it was a Moorish influence or something that started on that.
It came
I
from
wish I paid more attention now.
And of course, if you take an astrolabe and you make a mechanical model where the planets actually move in their paths, it's called an orrery. So that's the difference between an astrolabe and an orrery. An astrolabe is static, and an orrery is mechanical. Things move. So this was Eratosthenes, but poor guy, as he got older, he contracted an eye condition called ophthalmia, and in later life it made him blind, and he was so depressed that he wasn't able to observe nature anymore, that he killed himself by starving himself to death. And he died in Alexandria at the age of 82 in 194 BC.
That's such a sad ending for somebody.
Yeah, so somebody who'd done things, so many years ahead of anybody else. So there you are, Mr. Eratosthenes.
That's fascinating. Yeah,
gave us so much science.
It's like we said before, all this knowledge that was there around about at the time. And a lot of it's been lost to us. And
well, a lot obviously in this case, a lot of it was lost because the library in Alexandria burnt down. Yeah.
I mean, there was. I was going to say, I think about something about last week, when we were talking about my chap. What was his name?
Democritus.
Democritus, yeah, I knew it had something to do with democracy. Democritus, because a lot of his work was lost, but that was due to neglect. But along the same lines, I was thinking, what happened in Alexandria with that when that library went up? With so much was lost.
Well, it makes you wonder how history would have turned out had that fire on that night in Alexandria not happened.
Yeah.
It's quite a thought, isn't it?
Because there's also I'm trying to think. There's a country in Africa where Timbuktu is. What country is that? Is that I can't remember now. But there, apparently, they've got a tradition of that they collect ancient manuscripts and books, and they basically hide them. And apparently the families, they all get together. They've got all these old books. They've come through the families, and then they basically keep them. Nobody can see them and all that. I saw a documentary about it, and these books go back, centuries and things like that. They're all sort of like astronomy books, physics. Mathematics and stuff like that. And of course, because they're not looked after properly, usually they're sort of like kept in a repository somewhere, and they're just totally bricked up, but there's no climate control or anything like that. And but it's like the family jewels. They won't let anybody see it or touch it.
Wow.
But there's a big civil war going on, and unfortunately some of these hiding places have been found and they've been destroyed. So again, we've still got this problem, because it was the same in Afghanistan, wasn't it, where the Taliban blew up all the statues and that were cut into the cliff faces and stuff like that. Yeah, it's such a shame. It's such a shame that something like this happened. But he was a very interesting chap. He was, and a very busy chap as well. And he knew his stuff apparently. So yeah, well done. That was a good one.
Yeah. It makes you think. We've got parallels with the Great Library of Alexandria, because so much of today's knowledge is on the internet. Yeah. And I'm not saying it's only on the internet, but if the internet were to suffer a global outage tomorrow,
exactly.
How much would we lose? And this is why it's important for us to keep producing books, And
exactly. Yeah, my sentiments exactly.
And even if you look at our digital media, how much has been lost already? going from, film to videotape to hard disks to CDs to DVDs to Blu-ray. And now all of those media have more or less disappeared, and we're just really left with the internet where everything is stored.
Exactly.
So,
I mean, all it takes is one big solar flare and we could lose the whole lot.
That's right.
Yeah. We could literally lose civilization in a few minutes.
We could. And we know from history that these solar events do happen.
Yeah, exactly.
So, we really, really are treading a very dangerous path by not doing more to conserve our knowledge as a civilization. That will be the equivalent of the library in Alexandria burning down. There we are.
It's like what I was just going to say, just to finish off, like we say, everything's on the internet and all that, but also the students of today have lost the knack of searching for something.
Yes.
They can find it instantly, but they couldn't go into a library and know where to look and how to look things up. And if it's not there in front of them on a screen, then obviously they think it's not important enough to know. But it's just the general practice of we search papers and then we'll reference something else and things like that. But with them, it's just if it's not on the screen, then they can't be bothered to actually follow these things up. So we'd lose a lot more.
Yeah, absolutely. Yeah. And it's funny to say that, because I, as part of my work this afternoon, I was actually hunting down some medical papers on the internet that I needed to find for references. And you need to know how to look for stuff. And so many people. They do a quick hunt in Google. They take the first hit in Google and think that's going to be exactly what I want. And that is reliable and accurate and everything else. And people also have lost the ability to critically evaluate information to find out, to say, is that actually true or not? And this goes back to Mr. Eratosthenes, because he did calculate the circumference of the Earth 3,000 years ago and demonstrated unequivocally that the Earth was a globe. And yet we've known that, unequivocally for 3,000 years. And yet there's this growing movement of idiots who think that the Earth is flat, and for this reason, because they don't have the mental machinery to critically evaluate information. And you can't blame them in a lot of cases, because those skills are not taught in schools.
Exactly. Yeah. I mean, there is the danger. That you say about the flat Earth people. There's also the people who are anti-Darwinism.
Yes, absolutely.
And things like that. And
it's the same thing.
It becomes we use the word dangerous when people start saying you should ban the teachings of this, that, and the other.
Yeah.
We won't get too political, but it's a sad state of affairs when people start shouting down. Everything's open for debate.
Yes.
But once you start saying we're going to ban this, we're going to ban that, that's not debate. That is just we know what the Nazis were good at burning books.
Yeah, absolutely.
So we don't want to go down that road.
Slope. Yeah. But once you have seemingly large numbers of people now that are detached from reality, who will not open their minds to anybody having a different opinion or viewpoint from themselves, you are in a very dangerous position, in my opinion.
Yeah.
So, and I don't know how this is going to turn out, because it worries the hell out of me. You're going along that thing. I know we're getting away from astronomy, but the things about people's rights and things like that, some people think their rights are overshadow everybody else's. So it's a worrying state of affairs, and sometimes these people are given too much advertising and stuff like that. As somebody once says, you have an unalienable right to your own opinions, but you do not have the right to your own facts.
Yeah.
So that says it all. Okay, then, Daz.
I think we'll leave it there.
Leave it there. We might pick up the discussion. So over to you.
Okay then. Oh, sorry. See, I got so involved in that one. Right. The next one I will bring up, and again, as I said, there is a tenuous link to what I was saying earlier on, and it is Einstein rings.
Einstein rings, fantastic.
Einstein rings, yeah. Now, Einstein predicted, because he gave us the fabric of space and time, that basically light will also be affected by gravity. And what he predicted was that if you had 3 objects in a row, and then you had one object behind another, so with the first object couldn't see it, that if it was far enough away and it was projecting light, the item in the middle, the object in the middle, will actually, if it had enough mass, bend the light so you could see what was behind the middle object.
Yes.
And he has been proved right. And we usually call it micro lensing or gravitational lensing.
Yeah.
They have been imaged by things like Hubble, and things and telescopes like that, but of course they're in space, and these things are usually far off, but you tend to see it most in galaxy clusters, because you've got the mass in that there.
Yeah, a lot of gravity.
Yeah, a lot of gravity. But also it was because what they saw is that around some of these galaxies that were between us and the background had arcs around them, rings.
Yes.
And then they suddenly realized, well, hang about, these could be these gravitational lensing that's been going on. And what they found out is that was exactly what was going on. We could see the galaxy that was behind the galaxy in the front. So what it is, the light, as we all know, light travels in a straight line, but it can be deflected by gravity itself. So the gravity of the galaxy in between us and the third object gets bent, and it lenses onto the Earth, so we can actually see it then. And it was also one of the reasons, because when they looked at the galaxy that was in the middle doing the lensing, that basically there wasn't enough mass to actually do this to the light, to bend it and to focus it onto where we are. And this is where one of the pieces of evidence for dark matter. There must be something else involved in these galaxies that gives it the mass to bend the light as it does.
Yeah, because if you take the mass or the visible mass of the galaxy alone, it's not enough.
Exactly. And that's exactly what it is. So basically, Einstein rings, and it can also be used with stars. If you've got stars which are closer to you, with a lot of quite a big star, then you can actually sometimes see the stars that are actually beyond it. And in fact, they also get a bit of a boost in brightness due to the gravitational lensing. So they will actually,
right, they do. Yeah, indeed,
appear brighter behind. And just a quick story. As you know, Andy, I use robotic telescopes around the world. And about 12 months ago, it was during the pandemic we actually finished it, but for about a year before, we were collecting data about on an Einstein ring. So what we were doing every night, we were setting up missions. There was probably about 12, 15 of us setting up missions, one after the other. And we were focusing on, I can't remember the number of it, but it was basically, we know where there was an Einstein ring. Now, this thing was way off in the distance and all that. And we're not using massive telescopes, but between us, over about almost a year, because of course there was a period when we couldn't image it and things like that, we collected data, and we ended up with basically hundreds of hours of data. And then one of my colleagues sat there and he put it all together, tweaked it, and then after about a year's collection of data, we had it. There was a little dot in the middle, which was the galaxy that was between us and them, and around it you could actually see the ring. Now, on the site I was using, this was the furthest object that had been captured using their telescopes. But that didn't last long. 2 weeks later, someone caught a quasar further off.
Oh no!
So that knocked us on the head. So, but yes, so that's what Einstein rings are. Is basically it's where micro lensing is where a macro lensing is where basically the light is bent around an object between you and the original object, and you can actually see it from behind.
Wow.
And then there could be a little bit more on that later.
Oh, okay. I'll look forward to that. The other thing, of course, you can have is Einstein crosses, where you don't get the image of a galaxy sort of smeared out into a ring or a partial ring, if you like. You see an image of a distant object that's being, whose light is being bent by a massive foreground object like a galaxy or cluster of galaxies, as point sources instead of a sort of a smeared out ring. And in fact, I was looking at an image only yesterday, which was fascinating, and it's 5 quasars, and they're all the same quasar. And,
okay, yeah.
5 separate images of the same object because the light has been bent around a more massive object in the foreground. Which is quite amazing. Mind you, we must point out, as I think we did last week, that light only ever travels in straight lines.
Yes, yeah.
It's the space that the light is traveling through that gets bent, not the light itself. Yeah. You can never get light to travel in anything other than a straight line.
No,
it's just not interested in doing that. And space, well, what we call and what Einstein called space-time, the continuum that the light travels through, that's what's being bent by the gravity, not the light itself. That's right. The light still thinks it's traveling in a straight line, but the path it's traveling through is curved. So that's
where we get our, was it geodesics or what they call
absolutely.
Yeah.
And
as we which is the line that it's following, it thinks it's in a straight line all the time.
Yeah.
Even though it could be going round in a circle.
Yeah.
Excellent.
Very excellent. And this brings us on very nicely to my next topic. E is for event horizon. Now, why is this relevant? Well, the event horizon is the area around a black hole, whereby if you pass this edge, if you like, you're never coming back. That nothing can bring you back because you would need to be traveling faster than the speed of light to come out. Now, what this means is the event horizon hides what's inside the black hole because no light can escape. For reasons we talked about last week, it's the same thing, the space-time being bent round in a circle so that light can never leave the black hole. But it's important to realize the event horizon is not a thing, it's just a place. It's a boundary. And once you cross that boundary, even by a millimeter, no power on the Earth can bring you out again. So this is the event horizon. And if you could see the black hole from up close, it would look like a black sphere. And that boundary, if you like, is the event horizon. Now, if you were to cross it, you wouldn't notice anything different whatsoever. But as you got into the black hole, time would slow down, or the time for an observer would slow down. Your clock would run as normal, but time for an observer would slow down. So they would never actually see you enter the black hole. You would be frozen as an image at the event horizon. In fact, you probably couldn't be seen because the photons reflecting off you would be so redshifted that the image would be so dim that you'd be invisible. But theoretically, the image of you is still there and it will be there forever. As you get further towards the center of the black hole, then you looking out of the black hole would see time greatly accelerated, and you would see the whole history of the universe passing in front of your eyes like a speed-up movie, which is an incredible thought. Now, this is all purely theoretical. Of course, it comes out of Mr. Einstein's maths, comes out of the maths of relativity, but all we need to say is that, beyond the event horizon, it's a pretty weird place. Yeah. And there have been estimates as to how long you could survive after passing the event horizon. And it does depend on the mass of the black hole. But if you were in an extra large black hole, like a supermassive black hole, you could theoretically survive for a few hours. And what happens to you then is that there's a gravitational potential, a gravitational difference, if you like, between your feet and your head. So if you're falling feet first into the black hole, that difference would slowly accumulate and it would start pulling you and stretching you and eventually pull you apart in a process that's known as, predictably, spaghettification. And that's what would await anybody going to black hole, spaghettification. And there's probably no way around it. And I say probably because, again, this is all theoretical. We may have got it wrong, but everything indicates that you couldn't survive passing the event horizon of a black hole. So there we are. So that's the event horizon.
Yeah, because you were saying, I was going to ask you about this business where somebody watching you fall into the black hole, you would stop at the event horizon.
You would stop at the event horizon.
And that's what they would see. They would never actually see you pass into the event horizon.
No, that's right.
Because, like I say, time shift and the way time works around gravity. And it's one of those things that I have trouble getting my head around.
Well, you're not the only one, Daz.
Yeah. It's like if you're in a very tall building, somebody closer to the center of the Earth is getting older faster than you are at the top. And
no, it's the other way around. They're getting old slower.
Oh, is it? Okay, then.
Yeah.
All right. Lay on the ground. Stay pretty.
Well, I've always said to people about this, if you want to stay young longer, start digging. Because the closest you get to the center of gravity, which with the Earth is the center of the Earth, the closer you get to the center of the Earth, the slower time passes relative to an observer. And of course, they proved this categorically in the 1970s. When they sent they had two atomic clocks and they synchronized each other so they were both telling exactly the same time. They sent one up in a high-flying aircraft traveling at speed around the world, and when they landed again, the two clocks were showing different times. The difference is minuscule because the gravity of the Earth is tiny, squillionths of a second, but there is a difference, and that demonstrated conclusively that old Albert was right, that gravity slows down time. Because
it's amazing. Because as I said, I struggle to understand it. I got it around the wrong way. But it's just how when you're traveling through space time and stuff like that, and how you age differently in different parts. It's just one of those things that just blows your mind. And,
absolutely.
It's like most things with physics and all that you've got to be able to think outside the box, and you just can't imagine.
Which is exactly what Einstein was good at, of course.
Yeah, exactly.
There we are. Yeah, so there we are. So that's the event horizon of a black hole.
Do you know what an endolith is?
An endolith?
Yeah, an endolith.
Well, I would guess lith is something to do with stones.
Yeah.
Endolith inside, perhaps? Inside stones?
Basically what an endolith is that it's a plant or a bacteria or a mold or anything that lives on or inside stones.
Really?
And yes, and this was going to be one of my C's, but we didn't get time to do it. So I'll just give you a quick rundown of what they are. So E is for endolith. It's deserts are extremely dry and can be either hot or cold, which of course they can be.
Yeah, because Antarctica is the world's biggest desert.
Yeah, exactly. The water is always the limiting factor in such ecosystems. So basically, the amount of water depends on whether or not it's a desert or not. There's an area on the south of on the English coast and all that gets so little rainfall, it is actually considered a desert. And the Atacama Desert in Chile is one of the hottest and driest areas, while the coldest and driest places on Earth are so-called dry valleys of Antarctica, as you said.
Yes.
The primary inhabitants of both kinds of desert ecosystems are bacteria, algae, or fungi, and live on or a few millimeters below the surface of rocks. Organisms that have adapted to living on or beneath the surface of rocks are referred to as endoliths, meaning literally within a rock. So you were correct. Yeah.
I was.
Well worked out, that was. Those that exist a few millimeters below the surface of a rock are also called cryptoendoliths. And basically what they are is they live just a few millimeters below the surface of the rock. And you can see these pictures of these rocks if you look on the internet. And literally just a couple of 2 or 3 millimeters below the surface, you will see a layer of colored rock, and it can either be green, sometimes it depends upon, it could be red or anything like that. And of course, if they're green, that possibly means that they're living through photosynthesis.
Of course.
So that means the light is actually getting through the surface.
I was going to say, how does light get through the surface of the rock?
Exactly. So there must, if it's using photosynthesis, then it's then the light must be coming through just enough for it to be able to perform its thing.
I suppose if the rock had a high quartz content, for example.
Exactly. It's probably something that's not going to be highly packed, compact, things like that. So it's going to
that's amazing. That's amazing.
And it's basically, and again, this goes back to like I said, searching for life on other planets. That just looking at things doesn't mean that it isn't there. There could be something inside the rock. And of course, because they're inside the rock, it basically protects them from extreme extreme temperatures, and also ultraviolet protection, which could be lethal for it. So of course that means on other planets where there's no atmosphere or the high exposure of ultraviolet,
like Mars, for example.
Like Mars, exactly. They could be within the rocks. So we don't only want to be digging into the soil and all that. We need to be cracking some of these rocks open, and maybe, because it was funny because I know you've been following our great glorious leader Pete's adventure with doing the rocks of Mars,
the image processing. Yes, the processing. He's doing a fantastic job doing that.
Doing a fantastic job. But I did notice on one the other day that I know is slightly in shade, but actually at the base of the rock, it had been sort of like a little bit undercut by
wind,
the wind in the sand and all that. But it almost looked as though there was a green layer lying underneath it there. So I could be wrong, but it's just these pictures that are coming back, we can see the mineral inside the rocks. We can see that they've been water eroded and sandblasted by the sand. And although we'd say sandblasted, that's not really correct, because a so-called high wind on Mars is sort of like a stiff breeze.
Yes,
at the best of times.
That's
but over years, you would still get the same effect because there's no atmosphere and things like that. It picks up the dust and it still acts like a sandpaper on these things.
Right.
But it's the endoliths. So D was for E. E was. He was for endoliths, little critters that live inside or on or inside stones, which is I found really fascinating.
Thank you very much for that. I've never really thought about that before. But of course, the Curiosity rover and Endurance are busy drilling into stones.
Yeah, exactly.
And taking samples and returning them to the onboard laboratory on board the rovers, which does the analysis. So I would expect them to pick anything up that looked a bit out of the ordinary, like endoliths, because their chemical signature, I would think, would give them away. But we don't know. We don't know what to look for, really. So there we are. Okay, right. Back to me, I guess. So I talked about the event horizon. I now just want to say a very short bit about the Event Horizon Telescope. E for Event Horizon Telescope. Now, this was the global array of radio telescopes that took the famous iconic image of the black hole at the center of M87. And it was an incredible technological achievement. Now, firstly, we know, because we've talked about this, that Sir Martin Ryle, famous British astronomer, was the man who invented all the maths behind the very long baseline interferometry, which was the technique used to link the radio telescopes together so that they effectively formed one giant telescope the size of the Earth. One of the restrictions of VLBI is that you need to know the distance between the telescopes very, very accurately. Now, with VLBI, telescopes are arranged in pairs in the array. So one radio telescope would be paired with another, which would be paired with another, and so on. And the distance between the radio telescopes, and they were all over the Earth, and they are all over the Earth in the case of the Event Horizon Telescope, the distance between those telescopes needs to be known to millimeter accuracy. If it's wrong, the VLBI technique does not work. And the giant virtual telescope that VLBI creates is useless. So that brings us to the question, what bit of the telescope needs to be known to millimeter accuracy? Because they're big beasts, radio telescopes, as we know.
Exactly, yeah.
And it turns out that it's the focal point where the radio waves focus on the dish of the telescope. And it's that point that needs to be known to extreme accuracy, down to the nearest millimeter. Otherwise, VLBI just doesn't work. And they use all sorts of techniques, from GPS to ranging from satellites to all sorts of things to measure that distance. But the thing is about the Event Horizon Telescope is that it wasn't quite that easy. They had problems. You'd think, well, knowing the distance between two objects, that can't be that difficult if you achieve that measure of accuracy down to the nearest millimeter. For example, the South Pole Telescope, which was one of the telescopes in the array, it's on ice, and the ice moves. So they had to adjust for that in their calculations. The fact that the ice was moving, they needed to know in which direction it was moving, how fast it was moving. So that was quite a technical challenge on its own. Also, did you know, Daz, that the moon's gravity pulls on the surface of the Earth and can change its altitude by several feet as the moon goes around in its orbit? Yeah. So what they also found with the telescopes in the array, that their altitude kept changing, and therefore the distance between the telescopes kept changing. So that had to be built into their calculations as well. Also, what they hadn't thought about was the telescopes at high altitude, particularly in Chile, where the ALMA array was used, but they had lots of other telescopes, the best place on tops of mountains, basically. And what they found was that the computers kept overheating. And the computers were overheating because at that altitude, you think how your PC is cooled. It's cooled with a fan. The air is too thin for the fan to pump enough air around the computer to keep it cool. So they had to come up with a new cooling system for the computers that didn't involve fans. And it, this is just an indication of what an incredible technical challenge it was. Also, during the observing run, where they observed for 4 out of 5 nights, 4 out of 5 days, because with radio astronomy, it doesn't matter whether it's daytime or nighttime. And it was a requirement that the weather had to be good at all of the observing sites around the world at the same time. Now, you might think, well, radio astronomy, what does it matter if it's cloudy or raining? It doesn't make a difference. Yes, it does, because when you have a low pressure area, that changes the refractive index of the air, which affects the signals that you're receiving. So this is why they had to wait until they had good weather at all of the sites around the world so they could do the observations. Now, for the future, this means that their viewing windows, if you like, are going to be limited primarily by the weather, because they will need good weather. They need high pressure areas at all of the observing sites. And as the Event Horizon Telescope grows, and they've added another, I think it's another 3 dishes to it since they took the famous image of M87, that's going to get even more difficult to have a time when, basically the whole world has got good weather.
Good one, yeah.
So this is why I think that people don't realize that the Event Horizon Telescope that took that amazing first image of a black hole was such an incredible technical achievement. They have been working on it for over a decade, but the thing about the computers overheating, they hadn't thought of, and it only really popped up at last moment. So they had to do that in a rush. But they did have a decade to, get all the maths and the science worked out. And it was an incredible achievement. So that's the Event Horizon Telescope.
Yeah, because because I didn't know about the land bulge, which is it's basically like the same as the tides on the.
Yeah, it is. It's a tide on ground rather than in the sea. Yeah.
And of course, with the Antarctic, you will find that you would get the bulge on the actual bedrock. And also on the ice as well. So, it would make quite a bit of difference. You said they've added some more telescopes to it.
Yes.
Does that mean, would they possibly be able to, I know it would be a disadvantage, but if there was, say, like 6 with really good weather, could they drop, say, the 7th off?
Very possibly, yes. It would mean that they would get lower resolution.
Yeah, of course. Because the more
it's all about. It's all about resolution.
That's right. Yeah, the more you can get on there, the better.
And they really want to produce higher resolution, obviously, as time goes on. Incidentally, the ones that have been added since the observing run of 2017, which gave us the image of the black hole, they've added the Greenland telescope. They've added one in the south of France and another one in Arizona.
Excellent.
And also, while we're on the subject of the Event Horizon Telescope, the Event Horizon Telescope did image the black hole at the center of our own galaxy, the Milky Way, 4 million times the mass of our sun, as you know, during the same observing run. But they haven't yet produced the image from it. And there's a reason for that, is because the Milky Way black hole at the center of our galaxy is 26,000 light years away. Now, that is astronomically not even as far as the corner shop. That's just next door. And because of our vantage point, we see a lot of activity around that black hole. There's a lot of gas swirling around it. There are stars. There's a lot of activity, and they found it very difficult to create a still image because everything's moving. It's like trying to take a photo of a moving car. However, I was reading recently that they do hope to come up with an image of the black hole at the center of our galaxy and release it to the public before the end of this year.
Excellent. That's something to look forward to.
So we've got that to look forward to. Because, you see, what we desperately need is a comparison with the one in M87. Because that will verify the technique, first of all. It will show that image was real, that, and they did go to extraordinary lengths to make sure that they got a real image, that we had an image of what was really there, not what we wanted to see. And we'll talk another time about the lengths they went to try and rule human subjectivity out of it. But if we have a comparison with another black hole, that will be so exciting. 2 black holes.
Yeah, exactly.
2 supermassive black holes compared. That is going to be amazing. So keep your eyes open for that.
So where do you stand on the latest theory that there isn't a black hole at the center of the Milky Way and it's dark matter?
Well,
keep it clean.
Fine. Give us the evidence. Show us some observational evidence for it.
Yeah, because I saw that come up the other day.
I mean, people over the years have come up with all sorts of weird explanations for what is there if it's not a black hole. And who was it? Was it Asimov or somebody once said, if a black hole suddenly stuck out a sign saying last Coca-Cola for 300 light years, nobody would be surprised. Because they are such bizarre objects. However, there's this thing about it being made of these particles and dark particles and whatever. Yeah. And I thought, that's fine, theorize. I mean, that's what science should be doing.
That's exactly. You did say that they tried to rule out people's
subjectivity.
Am I right in that I heard that they gave it to 3 different teams?
They gave it to 3 teams. of imaging experts. None of the members of the team were even aware that there were other teams, and they certainly didn't know who was in the teams. And when they got together for the first time in June of 2018, I think, they had a meeting. They got together for the first time, the three teams, and compared results. And all three teams had come up with roughly the same image. And that really ruled out the possibility, or largely ruled out the possibility, that they had subconsciously processed the image so that we ended up with what everybody thinks is a black hole that looks like a black hole. And that, that was a control, basically. Every scientific experiment should have a control, and that was the control. So there we are. So that's the Event Horizon Telescope.
Basically, E is for Arthur Eddington.
Ah, good old Arthur Eddington.
Now this all links back to Mr. Einstein and gravitational lensing and things like that. And it's about an eclipse. On the 11th of August 1999, the skies above Albert Einstein's birthplace in the city of Ulm in Germany darkened as the moon eclipsed the sun. It was a fitting tribute to the man who transformed our picture of the natural world, and an unlikely one too. Although a total eclipse occurs roughly every 18 months somewhere in the world at a given location, the gap between successive eclipses is about 350 years. What were the chances then that the greatest scientists of the 20th century should be commemorated by the last total eclipse of the millennium? But perhaps you should not be too surprised about the coincidence, for Einstein's eclipses have always been lucky. Take the pivotal role played by a similar total eclipse nearly 100 years ago in establishing Einstein's general theory of relativity. Einstein's paper, smuggled out of Germany during the First World War, reached the British physicist Arthur Eddington at Cambridge. It was Eddington who realized that the total eclipse of 29th of May 1919 would occur above the island of Principe off the coast of West Africa would offer a golden opportunity to test one of the general relativity's central predictions. Eddington's team traveled to Principe and duly photographed their quarry. They wanted to observe a bright cluster of stars called the Hyades, which is in Taurus, as the sun passed in front of them. To blot out the solar glare, Eddington needed a total eclipse. If Einstein's theory was correct, the positions of the stars in the Hyades would appear to shift by about 1/2000th of a degree. That's quite small, isn't it?
It's tiny. It's tiny.
Eddington first took a picture of the Hyades at night from Oxford, and then on the 29th of May 1919 he photographed the Hyades from Principe as they lay almost directly behind the sun. It took a long time to detect this bending of light. The shift in the position of the stars was so small, but in September 1919 Eddington finally announced that Einstein was right, comparing the two measurements. Eddington found that the shift was as Einstein had predicted. The result turned Einstein into an international superstar.
It did indeed.
So basically, what we were talking about earlier on, the gravitational lensing was proven then. But even now, even to this day, people still question the results. It's been proven time and time again, and we were talking about this a little while ago. It's been proven time and time again that the light is bent by anything massive with enough gravitational pull that it can actually bend space-time, so that the light would appear to bend. So what else we got? It just says that. It says it still causes controversy today. The bending of light was actually too small for Eddington to have been.
Yes, I'd read that his telescope wasn't accurate enough to see that bending of the light.
Yeah, so that's what they've said. But it's been proven time and time again.
Yeah. And in fact, if you look at Einstein in general, all of his predictions. I don't think there are any outstanding, but I think all of his predictions, more or less, have been verified by countless thousands of observations, and then really not up for question. And these people who say, "Oh no, Einstein was wrong," they're just delusional.
Exactly. I mean, it's Einstein's equations and his theories that have been proven time and time again. He predicted gravitational waves, and of course we've detected those now with LIGOs, the 2 LIGOs in America, and Virgo. I can't remember the name.
And just returning to that image of the black hole in M87 for a moment, the orange ring surrounding it. We should say that the ring isn't really orange; it's the color that the Event Horizon Telescope team chose to represent radio waves. Radio waves are invisible, so we don't see the color of radio waves. So they had to choose a color, and they went through various color combinations. Thank God they didn't choose pink. That's all I can say. But they chose orange. Anyway, that orange ring in the image, the bottom of the ring is brighter than the top because it's moving towards us. So the ring is at a slight angle to the Earth. And Einstein predicted there's this thing called Doppler beaming, where light moving towards us has a higher apparent energy than light moving away from us. And you can see that brightness difference in the ring around the M87 black hole.
Because don't they also, with further analysis, think they've detected the photon ring?
So what they've detected is polarization in that light. And that is an indicator of where the magnetic field of the black hole is, which is extremely exciting because it gives us our first real basis for investigation into the magnetic field surrounding a black hole, because nobody really knows why black holes have magnetic fields in the first place. We don't know what causes them. We don't know much about them. So the fact that they realize that light around the black hole was polarized enabled them to not exactly map the magnetic field, but show roughly in which direction it was pointing. So very, very interesting stuff indeed.
Excellent. Okay,
so anything else about Mr. Eddington we need to know?
No, that was basically it. I was
right.
linking him to Mr. Einstein. So, as I said, there's several links that, virtually everything comes back to Einstein.
Absolutely.
So,
okay, thank you for that, Mr. Arthur Eddington, famous astronomer of the 20th century. I've got a really short one for you now, Daz. This is quite interesting. Eridanus. E is for Eridanus. And I've always pronounced it Eridanus, so you might want to call it Eridanus or some variation. Eridanus it was one of the 48 original constellations. It's a southern hemisphere constellation. You can't see it from the northern hemisphere, but it was one of Ptolemy's original 48 constellations, and it made it through to the current list of 88 constellations. It's the 6th largest constellation in the sky, believe it or not. It's what's interesting about it is that it contains a void, a space, a gap, if you like, which is enormous. It's known as the Eridanus supervoid, believe it or not. And what these areas in the universe are, they're areas where there are no galaxies, and we're not quite sure why. The Eridanus supervoid was discovered in 2007. And it's huge. It's about 1 billion light years across. So there's an area of the universe 1 billion light years across where there are no galaxies. And it's the second biggest void. It actually is a bigger one in Canis Venatici, which is bigger.
Oh, that's the one I can't say, isn't it?
That's the one you can't say. And we're not going to ask you to say it again, Daz, so as not to
Canis Venatici.
Well done. Interestingly, the Eridanus supervoid is linked directly to the cosmic microwave background, because that void is in the cosmic microwave background.
Okay.
So in other words, this is not a recent phenomenon. It's not as if there used to be galaxies there and they've sort of drifted apart, causing this void 1 billion light years across. There were never any galaxies in the Eridanus supervoid. Well, not 380,000 years after the Big Bang forwards, which is when the CMB dates from. But some people have suggested this is a place where our universe is touching another universe, and this would explain the void. We don't have any explanations as to why an area, for example, in this case, 1 billion light years across, could end up with no galaxies. And we don't have an explanation for that. So that is interesting. What's going on with these super voids, like the one in Eridanus and the bigger one in Canis Venatici? So that's Eridanus for you.
Yeah, because you say about this, I think I mentioned it on one of my other programs and all that these, as you said, they think that possibly these voids have been created or there is a bruise of us bumping up
against another universe.
Another universe. Yes. Because the multi-universe, and they think they're sort of like bubbles. Yes. And they can touch each other and things like that. And the thing is, and I think I talked, I can't remember who it was. Was it Mr. Rees, Professor Rees?
Could be.
Was talking about black hole, this beginning of the universe, and he basically says it repeats itself.
Right.
That eventually everything will enter a black hole, and then it will all sort of like pop out the other side.
Right.
And I thought when he was talking, he said it ends up like the universe will do almost exactly the same on the other side, go through all the same thing again. So you end up like a row of sausages.
Right. I see.
That. And I thought, well, yeah, it was a bit more complicated than that. So, but you end up with sort of like a picture of a row of sausages once you look at it. So it all ends up in a black hole, all condenses, and then it pops out the other side. Which could be the inflation. Yes. And I also thought when I heard about this bubble thing is maybe there was a rupture in the space-time and all the stuff from another universe popped into our universe. I don't know.
Or, conversely, the galaxies that were in our universe disappeared into the other universe, hence the void.
Well, exactly. Yeah.
The problem with all this, Daz, is this. Great. These are things worth investigating in science, but so many of these new ideas about the universe and the multiverse and, parallel universe, all this, we don't have any observational tests for them. No, there are no observations or tests that you could do to demonstrate that any of that is true. And this is unfortunately the way that physics is going, that we've reached a point in physics where we may have the answers, but we cannot test them, and therefore it isn't really science, or not what we think of science. We may need to rethink what we mean by science. We may need to say, look, we can't do observational tests, but this maths looks really, really correct. It looks really good.
Yeah.
Can we say it's true? Well, without testing it observationally, how?
That's right. It's scientific observation.
It's
and
not
then once you prove
method,
something there, you've then got to do scientific observation of that. And then it's got to be able to be backed up as well. So
and then you get into all sorts of philosophical questions, like if we have to rely on the maths, if we agree, if everybody working in the field looks at the maths and says, yeah, that must be true, that's absolutely spot on, how do we know that our maths is actually a physical representation of what actually goes on, that it's not just an analog, and then you get into lots of philosophical deep questions about meaning of reality and all that stuff. But for the moment, I'm just going to stick with the constellation of Eridanus because I'm on pretty safe ground.
That's right, because like you say, you've got the cosmic web, as they call it, and things like that, and that's that's weird enough, and that's all links up with the microwave background as well. Yeah. So
fascinating stuff.
It's fascinating. Stuff. Okay. Yeah, it's very good. Yeah, very good. Right. That's been a good week, actually. I've enjoyed this week.
Yeah, it's great. So we will say goodbye for this week. Thank you for listening to the amazing astronomical alphabet. We do hope you enjoyed it, don't we, Daz?
Yes, we certainly do.
We'll be back next week, and logically and naturally, we will be tackling the letter F next week. F for Freddy. So we hope you're going to tune in again and listen to the amazing astronomical alphabet, where we will be talking about things in the universe beginning with the letter F. until then, have a fantastic week and look after yourself. Stay safe.
Yes, and stay safe, and we'll see you soon.
And it's good night from me, and it's good night from him. So
bye.
Bye.